think it's still 190 or so. Yeah.
190 people in this lecture.
They're all here.
Even the live slides, there's not that much.
Oh.
That's probably something weird with OBS.
Here we go. Do you want to just present off of mine? Yeah, sure. Then we wouldn't be, yeah. Okay, if you can give me the clicker. Thank you. Yeah. Audio? Yeah. Stream up or? Alrighty. Alrighty, everybody. So we're going to be talking about variational autoencoders today. I know we've kind of touched on autoencoders in the past, but I'm going to do my best to, kind of bring you guys back a little bit from break and talk about VAEs and autoencoders in general. So a couple of things to remember about how neural networks work. There are two things going on in most neural networks. The first is a feature extraction setup, and the last step is a classification. So everything except for pretty much the last layer can be seen as a feature extraction of some sort, and then the last layer is using those features to perform classification. The idea being that everything up to those features, everything up to that classification layer can just be seen as separating the data, and then actually making the classification is the final layer. You can also use these networks for generating representations. So part of the idea of doing that feature generation is building out a representation for your data. We talked about this a little bit with autoencoders. We're going to dive into it pretty heavily today. But the idea is you can try and project your data into some vector space that would be informative for your classification. And so the idea, again, you've got your raw data over here. You've got your feature extraction network going on, doing whatever math it's been trained to do. And then here it's actually doing just linear separation in whatever space it's been projected into. So yeah, network learns features from layer 0 to n, or n-1, and then the final layer is used for classification. One of the interesting things to note about this is that when you're actually doing this sort of thing in industry, it's pretty common to actually just take your network, a pre-trained network on some big academic task, and then just lop off the top layer and retrain that last layer for whatever target you're actually working on in real life. So a lot of times you'll see, if you go to a company, you'll see somebody take some big CovNet or something and do that for their purposes. It's kind of nice because you can use the feature extraction setup and then just keep training models, training stuff on top of it. But yeah, so we can see it happening here. We've got our raw data here. We're extracting some features here, and then we're just performing linear classification in that dimension. So this is kind of a toy example, but I think it illustrates the point kind of well. So then autoencoders. This is kind of motivation for ways you can think about autoencoders and ways you can then think about how VAEs are going to be doing their thing. So autoencoders, you can think about it as doing a nonlinear PCA over your data. So basically, if you're minimizing the L2 divergence, you can see it as performing a nonlinear PCA or multiple PCAs stacked on top of each other. But the idea is that you take your data, you project it into some dimension. That dimension is then going to be some value which is going to capture the most variability of your data, so you can then try and regenerate the data on the other side of the autoencoder. And then as you keep adding more data, you're going to be trying to capture more and more variance, and so that's kind of just intuitively how you can think about you're doing PCA. Yeah, so you're going to be, for one dimension, you're going to be trying to capture the most amount of variability or the maximum energy. And so as long as you are actually minimizing your loss, you're going to be trying to capture that. So the other thing you can think about is that autoencoders are only capable of generating data that they've seen before, or data that's been given to them in their distribution, or in their training data. And so the data that you generate, it's called a manifold, but you can think about it as just, the only things that are capable of, your autoencoder is capable of generating, or any decoder is capable of generating, is data that's been, present in the training data, or at least drawn from the distribution of your training data. And yeah, every input will result in an output along that manifold. It's not like, if you throw in garbage, you're going to be getting some garbage out. You'll probably get something that at least looks like your training data, even if it's a little bit weird. And you can kind of see this effect in terms of denoising. So there's this concept called a denoising autoencoder. The idea is that you apply some noise to whatever input, and you can get a denoised version of it out. So this is just the raw version. This is the noisy version, and then this is what the the autoencoder generated on the other side. So this is kind of cool because your autoencoder is only capable of generating things that it's seen, and so if you give it something that's kind of like what it's seen, it's just going to do its best job to plop that into the training data space. So you can think about it as a source-specific generative dictionary. So it's only going to get things. It's only going to generate things that are look like its training data. Yeah. So then variational autoencoders. So that's just autoencoders in general. But as we can think about autoencoders in general performing PCA, we can think of VAEs as performing nonlinear factor analysis, which we're going to talk about a little bit and try and get some understanding for. The idea for VAEs is they get their name from variational inference, and you use that for parameter estimation. And so during the rest of the talk, we're going to talk about a little bit of generative models, sort of just the motivation for it and why they're, why you can think about them. Factor analysis, variational inference and expectation maximization, which is kind of the way that you train, and then VAEs in general. We're going to try and step through motivation and then actually get to VAEs. So hopefully when you see VAEs, it's going to make some sense, but that's kind of the idea. So types of models. There are two types of models in general. There's a discriminative model and a generative model. For a discriminative model, the idea is that you've got some distribution and you want to select from it. So this could be classification, so you're discriminating between your outputs. So classify this image as one of 10 different classes, or classify some image as a, as a number for MNIST, or as a class for CFAR. And then the idea for generative models is, actually generate the output. So given some input sequence, generate some output sequence. And so there's a little bit of the two of discriminative in the generative model. So you can think about it as, which if you're generating an image, you need to discriminate between the pixel value. But they're kind of lumped in terms of actually just regenerating the output. Yeah, we talked about both of them in class, but I don't think we've drawn this line before. We're going to talk about GANs later, and so this kind of distinction is going to be pretty important. But for the time being, just something to think about. Motivation for it, you can generate data sort of arbitrarily. So just given some garbage, or not some garbage, but some random input value to a decoder, you can generate data that it looks like it's drawn from your training distribution, which is pretty cool. And one of the reasons why these kind of have become so popular is because there's a lot of training data for generative models, while there isn't as much for discriminative models. So it's really easy to just associate two things and say that one is conditioned on the other. So like, yeah, video, there are comments on a video, so those comments are supposedly conditioned on a video and maybe some, mental state that the user has or something like that. But, it's a lot harder to get somebody to go out and label whether or not this image contains a bird or something like that. So when it comes to actually doing these things in the real world, it's a lot easier to get data for generative models than it is for discriminative models. And you can kind of apply soft labels to get those discriminative labels if you want, but that's kind of just look at it from this perspective. So here's an example. So people have been captioning images for a long time, encyclopedias and blah blah blah. So man in an orange jacket with sunglasses skis down a hill. You can also do things like generating a output image given an outline. So on the far right is the output that's coming out of the neural model, but on the input is the outline, so it can kind of do things that are interesting. But yeah, the other great example is really easy to generate training data for is super resolution. So you feed the model some de-resed version of your image, and you expect the full resolution out. And there have been a bunch of approaches of trying to do it. Bicubic is just what your Photoshop or whatever it does when you just scale up an image. But as you apply more fancy techniques, you can do cooler things. But this is just trying to motivate generative models. So the other cool things about it is it gives us insight to our data. So we can look at the data and say, this is what's coming out. This is what our training data looks like. So we can kind of think about it like that. OK, so with generative models kind of motivated a slight amount, we're going to talk about factor analysis. So we're going to assume that our generative models assume that the training data is generated from real values and latent variables, real valued latent variables. So you've got some distribution for your input data that gets mapped onto some vector, and that's where your latent variable space is going to be. Again, this is just kind of motivating everything. All right, so we've got xi and zi, which are real valued vectors, and one is going to be the x is going to be the observation, and the latent variable is going to be z. We're going to define a probability distribution for our latent variable, which is going to be over some Gaussian given the input and some standard deviation and the mean of the distribution. Pretty straightforward, I hope. And then we're going to do the same thing, but using our weights and that latent variable to generate the input given the latent variable. Pretty straightforward so far, I hope. Stop me if anybody has any questions, by the way, just shout it out. So this is just, we're not getting into models yet, we're just defining how we're going to represent our data. So we've got a latent variable and we've got an input, and this is how we're defining them. I know this math is kind of, there's going to be a lot of math in these next couple slides. I'm going to do my best to get through it and explain it pretty well. But if anybody's got any questions. So again, we're defining our input now as our model overall is the probability of x given the weights. We're going to define it as the integral of the two distributions that we just talked about before, latent variable and the input. And then we can rewrite this as just a normal distribution entirely. And then we can rewrite that again and rewrite it again. But this is kind of the derivation for it. And then the things that we can actually think about is that the probability of the latent variable is just going to be a normal distribution centered at 0, and the standard deviation is going to be the identity matrix. And then we're just going to be generating values off of that. while the input the probability of the input given the weights is going to be the input centered at some mu, which we haven't defined yet, using the psi that we talked about here, which is just going to be just a real valued thing, which we're going to, again, get into in a little bit, but we're just defining things right now. And then we're going to add weights to it. So far, again, we're just defining terms, but yeah. Okay, so now we know that the x given, px given the distribution and the weights is going to be defined as the normal distribution, kind of just what we said in the last slide, and the covariance matrix of the data distribution is broken into two terms. So now we've got two terms working here. This is just a rewrite of this. So we've got our mu, which is the mean of the distribution, and we've got our standard deviation, which is defined off of the weights and psi. We're just defining things. I know there's a lot of words, variables and things going out here, but we're just defining things. Psi is the variance. We don't care about that for the variables. It's just some predefined value. And then we've got a low rank matrix, which is the weights, and then this is the variance of our this is the variance due to the latent factors, meaning that this is the variance of the distribution given some latent factors which we haven't yet defined. I know there's a lot of setup to get into it, but this is just the idea. Okay, there's a special case of this which we're kind of going to breeze over. You can do probabilistic PCA using it. Yeah, special case of factor analysis. Basically, if you restrict psi to some value based on the identity matrix, you can kind of force factor analysis into doing a probabilistic PCA. But just something to think about. We're going to kind of skip through this. So now we've defined our variables. So if we jump back, we've got our P of x, probability of x given the weights, and we've got that defined as a distribution. So now what you can think about this is that whenever you have a class of objects, we've defined that class, that kind of representation space as a Gaussian. So the center of the Gaussian is going to be one class, and the center of some other Gaussian is going to be another class, and so on and so forth. So that's what these mu's are doing, is that you can think about them as being learned centers for data. So yeah. So we're going to learn we're going to learn those Gaussians, those parameters for those. We're going to learn the parameters for those Gaussians using expectation maximization. We're going to talk about. We're going to do a little bit of the derivation for EM. Yeah, we're going to bound it by. We're going to find a lower bound, the log likelihood, which is going to give us sort of the starting point, and then we're going to try and maximize it. Maximize that lower bound. So there's two steps to this. There's the expectation, which is where you're finding the lower bound, and then there's the maximization where you're trying to maximize that lower bound on your data. Okay, so we have two now we're not thinking about this anymore in terms of classification or anything like that. We're just thinking about it in terms of two distributions. So you've got two distributions, Q and Z. They're both given the same, the same input variable, and you want to calculate the divergence or the KL divergence between the two. So it's the integral of just the log. So this is just KL divergence. And so now we're going to rewrite the second variable as just conditioned on some input and some parameters, right? So you've got some target distribution, and then you've got some models, or something that came out of your model. So this is the target distribution, and then probability of z given x. KL divergence, and then we can rewrite that as this. Yeah, so we're going to be doing it with a yeah. So again, this is, you can think about this as coming out of your model, but it's just an arbitrary weighting distribution. So yeah. So now that we've got this guy, we can apply Bayes to it, expand it. We've got this coming out of it. And then we can reapply that back into the KL divergence, and we've got our whole expansion coming out over here. So the KL divergence of these two variables, QZ, your original distribution, and P of z given x and some parameters, is then just going to be defined as QZ, and then a bunch of log stuff is defined by Bayes. I know this stuff is kind of dry, but we'll get into the VAEs in a bit. But this is just trying to motivate the ideas behind factor analysis and then VAEs. Okay, rewrite the divergence. I don't want to get into all of this, but basically just the takeaway is that the KL divergence then becomes the KL divergence of QZ plus P of X and Z over some parameters, and then log of P of X given the parameters. So you've got KL plus some bias. That's the way you can think about it. So now we're going to talk about the evidence lower bound. So this is the idea that we're going to be trying to, this is the value that we're going to be trying to estimate and then maximize as time goes on throughout our optimization step. So we've got KL, which we've just defined as KL divergence plus some bias. And then we're going to rearrange the terms a little bit, break them into two, and just move one to the other side. So now we've got the bias, log of the bias, which is going to be equal to two different KL losses, right? So the evidence lower bound, which is going to be this L. I think some of the slides may have gotten messed up, so at some point you might see L as some weird squiggly line. I'll point it out when it happens, but yeah. Evidence lower bound gets rewritten as this, and then the log of P of X can be written as this. Again, this is just saying we're just relabeling things here. We're not doing any crazy math yet. So that's that. So now we've got the evidence for the lower bound, hopefully. And then we're going to rearrange things a little bit. So this is the value from the previous slide. We've got the, and now we're just defining this L value, this loss value, which is going to be loss of some Q, which is just the same Q that we've been using before. Q, I know we're kind of introducing a couple variables randomly here, but the idea is just Q is some new input value for this in the loss space where. I'm sorry, Q is just the distribution. It's just we remove the parentheses from it. So loss given distribution Q and the parameters theta, we're just doing rewrites at this point. So now we want to maximize. So we've got our lower bound, which is the loss value, which is coming from the KL divergence between the two distributions. And we've got the bias on top of that. Sometimes called the evidence. But yeah, so the idea is that we've got this value, and now we want to maximize that value. I've been calling it the loss, but just for to think about it. But this is a situation where you're going to want to be maximizing as opposed to minimizing. So yeah, when this bound is tight, when is this bound tight? Excuse me. When these two distributions are closely aligned. And so the idea is that you want to take these parameters theta and get this distribution to be as close to QZ as possible. So you're trying to maximize that value. If you can represent the distribution Q using the distribution P, or using probabilities P, then you're doing a good job of estimating your data. Yeah, sometimes called the variational bound as well. So all of that out of the way, the idea is just that you've got some distribution Q and you're trying to estimate it using using some input and some theta, and yeah. All right, so this is kind of how you can think about what's actually going on visually. I know we just stepped through the math. I know it was a little bit heavy, but the idea is that you've got your KL divergence, and you've got your loss here, and we're trying to get these two to be, you're trying to get this relationship here, QZ and P of Z given X and theta. You're trying to get those to be as close as possible. So when they are as close as possible, the KL divergence is going to be super tiny. So yeah, we've got loss here, which we're trying to maximize. We've got our KL divergence here, and we're trying to minimize that. So the way that we do this is using the expectation maximization algorithm. So the idea is that there's two steps. There's an E step, which is the expectation step. There's a maximization step, which is trying to maximize. So we estimate this value, and then we try and maximize it using theta, using the parameters theta, excuse me. So at each iteration, it's an iterative process. E step, we're going to fix theta, and then find a Q, which is an estimated value for Q, which maximizes the loss function, right? Then for M, we're going to hold that estimated Q fixed, and then find some theta, which is going to maximize it. All right, so we're estimating and then maximizing. So yeah, so we've got, again, we've got our loss, we've got our KL divergence, and then we've got the relationship between the two. First term does not involve Q, so this is the bias, and we can do, and we know the KL divergence must be non-negative, so we can't ever go over it. We can just approach it, and thus we can make it using theta. Using theta, we can try and get KL divergence to be as close to 0 as possible. So the solution is just to set our estimate for the Q distribution given Z, Q of Z. We're going to try and make those two as close as possible. And so what we do is we just do an argmax over the parameters for the loss, and then this just works out to being the argmax of this. So the idea is that, like I said, we've got our KL divergence, and we're trying to just push it up to the estimated value already. So then the M step, so a little bit more math here. So we've estimated our lower bound by using this estimation, or using the bias estimator, and then the relationship between the loss and the KL divergence. And then we need to, so now that we've estimated it, we need to maximize it. This is the derivation for it, but the takeaway is just that we're going to argmax theta, the expectation of this distribution. All right, so yeah, there are a couple of things we can this is the step-through process. Considering how much is in this slide deck, I'm going to try and whiz through it a little bit, but this is for your reference if you want to look back at it. So the M step, we're trying now to maximize it. Again, because the KL divergence can't be 0. If we overshoot it, it's just going to come back to it. Or go back, the sign's going to flip, so we don't need to worry about it. So now we're trying to maximize it. If we can push up the bias a little bit with this maximization, then we've got a little bit more KL divergence to work with, and we can go from there. Okay, so I know I'm kind of whizzing through this, but the idea is, E step, you're going to estimate you're going to estimate the relationship between the two distributions, and then at the M step, you're going to try and maximize that relationship as much as possible. So why does EM work? Yeah, this is just kind of defining the relationship between the two. So as long as the lower bound is tight, you're going to be modeling your data. So you can think about this as just trying to keep that relationship between your estimated values and your probability distribution as tight as possible. Okay. Yeah, this is just kind of a visual thing of what we've been talking about already. Okay. So now, oh man, I don't know what this is, but I mean, I'm sorry that's kind of displayed that way. But this is just going to be a summation of QZ over I to M, and there's another value which got dropped off here. I'm sorry about that. I'll make sure it gets fixed when we upload the slides. But basically, variational inference is now taking factor analysis, and we're going to be using the principles that we learned kind of to perform variational inference. So we're going to be optimizing loss of Q with respect to one of the terms while holding the others constant and repeating for all terms. I wish this equation would show up, but what can we do? So variational inference is very similar to, you're using the EM algorithm to try and push the two together, to try and push these two bounds as close to as possible. Yeah. All right, so I don't know if I want, so just given the amount of time we have, this is just I'll just leave this for reference. This is just another way of thinking about the EM algorithm, but I want to get into the VAE stuff, so we can go from there. This is just a continuation over the different perspective. All right, so factor analysis. So now we've got two distributions. So for simplicity, we can assume the data is centered because we're going to be learning some bias term eventually that's going to center those distributions as close as possible. And so we're going to do, to try and get that relationship as close as possible, we're going to do an argmax over the two, and you can just rewrite this as opposed to doing a log for all x, it's just the summation of the two. So for every training example, you're going to be trying to do that argmax, and you're going to be trying to push those bounds as close together as possible. And then we're going to rewrite this again because we know that the p of x given the weights and the psi that we talked about way at the beginning of the class is just the same as the normal distribution, which we talked about earlier. So now we're just trying to, we're taking the distributions that we had described at the beginning of class, and we're plugging them into this kind of algorithm. Yeah, no closed form solution. We have to do this iteratively. We've got to just take the data and step, and try and minimize that KL divergence. Yeah, so because psi and the weights are coupled together in the derivative, we can't solve for them analytically, so we need to minimize. Yeah, so now we've talked about EM. This is factor analysis. Now we need to combine the two. So this is kind of the steps, but this is just kind of the derivation. There are two things to consider. If you actually go to decide and implement this, you're going to be maximizing just W and psi, and then this is the equation that you're going to be maximizing. I know there's a lot of math, but there are two things to consider. In order to compute to be able to do the M step, we only need to be worried about the expectation of z of I given, the expectation of z of I given q, and then again, just a different value for z of I. So these two things only depend on the latent variables. Once we've got the E step done, we can then do the M step. Yeah, so here's the E step. These are the two expectations that we just talked about. These are the things you need to worry about. These are just kind of plug and play variables that we can think about as being from the derivation of factor analysis. Yeah, so this is the values for this expectation and then the second expectation. So we've got the weights for whatever time step, and then we've got psi for whatever time step. G is this distribution here, and the idea is just that we're going to be trying to nest the two. So back here, we've got E given z of I, and then that z of I is right here, and then this value right here is defined as the combination, combo of two different values from the above expectation. And then yeah, so G is just a constant which we define as that. It's going to change every time in your step, but that's how you do it. Then the M step, you're going to be updating W of t according to the summation of expectations, and then you're going to be updating psi of t according to this equation. So trying to think of a way to try and understand it. If you think about it in terms of, you can think about it as just in the end, it just kind of becomes a bit of a linear classifier, at least in your projection space. So you've got a W and an X, and you're just trying to draw a line between the two of them, plus some bias term. Yeah, so we're trying to maximize the relationship between the lower bound. So trying to get those two lines that we talked about before as close together as possible. Yeah, for variational inference, there's no distinction between hidden variables and parameters for distribution because the parameters for the distribution define how the model behaves. Yeah, and so this just means that as opposed to using theta, we just combine all of theta and put it into z, and we call those the parameters. Yeah. So now that we've got that defined, so this is the combination of variational expectation maximization being used in variational inference. So now that we've got that, we've got our weighting distribution L of Q, and we assume a form of Q that we can optimize. So basically, we've just we're trying to keep these two together. And then for the mean field theory, we assume that Q factorizes just according to this. So for all values in Z, there's some appropriate value coming out of Q that makes sense. We then optimize the two, and then we can approximate the two using some posterior probability distribution. This is the derivation. It's there for your reference. I'm not going to talk about it too much. But yeah, the takeaway is just the last line at the bottom for the mean field update. So yeah, then Q at time step t is just going to be based on the value of Q at time steps t is going to be defined for the value z sub j as this whole thing here. Yeah, the idea is that we're going to freeze some variables, compute expectations over them, and then update them using the expectations. So expectation maximization, we're going to take the values, approximate them, and then try and maximize those values to be as close to the lower bound as possible. So variational inference, it's basically just going to be this very similar argument as for what's going on with EM. But again, if we've got a loss, excuse me, if we've got a value that is defined off of some divergence KL, and if we're trying to squish that KL divergence to some estimated value as close as possible, then it's going to work at least somewhat well. We're going to be doing some form of optimization. Okay, so now with all of that out of the way, we can talk a little bit about the variational autoencoders. So we've got two parts of every VAE. The first is the encoder, and the second is the decoder. The encoder the decoder. This, for the purposes of these slides, this is going to be the decoder, and this is going to be the encoder. And we've got some latent variable z defined as a distribution of Q, given the latent the probability or the distribution, which we're trying to get the value z of j, given some input to the encoder and some parameters. Two things to notice: the parameters to these two are slightly different. We're going to be defining the parameters for the decoder as I think that's phi, and then the parameters for the encoder are going to be theta. So just keep an eye on that. All right, so the so the observed variable is distributed according to some conditional probability. So this is what we're trying to do. We're trying to predict x given some input, or excuse me, given some latent variable and some parameters. So basically, the core of that is just we're trying to do an autoencoder of some sort. Given some parameters and given some hidden representation, we're trying to predict the input. These values this is very similar to factor analysis in general, so we can try and kind of tie the two together a little bit. So we can also create the weighting distribution, which we talked about earlier. And that's going to be z of I given the input and some parameters phi. So one thing that may not be entirely clear in terms of the setup of the VAE is that when we're here in the encoder, we're trying to predict the latent variables given the inputs and some parameters, and then here we're trying to predict the input given some latent parameters and some theta. So we're no longer trying to predict the distinction. We're no longer trying to predict the input. We've got two different steps going on. We've got one to predict the latent variables and another to predict the actual input, right? Is anybody unclear on that? Because it's, no? Okay. So yeah, this is the, yeah, so we're going to construct the weighting distribution, QZ given x of I and theta, or excuse me, and phi, and they're going to play the same roles as Q of Z of I that we talked about in the EM algorithm. Yeah. The other thing is that in the EM algorithm that we talked about before, we described these distributions, these weighting distributions as Gaussians. So you've got a Gaussian centered at one point and another Gaussian centered at another point. You're trying to figure out which one is closest to each other, or you're trying to approximate classes based on which Gaussian each value is closest to. Gaussian is kind of a choice. You can use a different distribution if you'd like, but for the most part, people just use Gaussians because they find that it works pretty well. We're going to be using a Gaussian for the VAE in the slides, but again, it's kind of another hyperparameter that you can tune. So the thing to consider is that when we are working in a standard autoencoder, the latent variables that we're generating in our model are not necessarily tied well to the actual output of the data. There could be several parameters or several hidden values that are really highly correlated, but others that may be just garbage values and random. We're trying to take away from that a little bit by using the variational autoencoder. We're trying to attach different values to each parameter in the latent distribution so that we can actually fiddle with what's going on and make sure it gets the best value. Yeah, so we want to be able to encode our data into the latent variable space. The conditioning, the weighing, this conditional weighting distribution enables that encoding. So one of the cool things about this weighting distribution that we're deciding, this Gaussian or something like that, is that we can kind of inject a little bit of domain knowledge. So let's say that we know already that our data follows a Gaussian, then we can use a Gaussian. But if we know that it follows some other distribution, one that we've either predicted or estimated, we can use that as well. Okay, so to implement these two, we're going to be using an encoder-decoder model. We've got the encoder, which is going to be the, it's going to read the data and generate some representation. And then we've got the decoder, which is going to take that representation and try and decode it into some space. And then the way that we're going to do this is we're going to take that Gaussian in the middle, or what have you. I'm just going to refer to it as a Gaussian. We're going to draw a sample from it. So this Z of I is actually a sample from some distribution. Yeah. So again, just to clarify, decoders up here, we're decoding X of I given Z of I and some theta, and we're encoding some latent variable given some input and some phi. This is what it actually is going to look like under the hood. So there could be any number of layers between the inputs and whatever's going on, but the idea is you're going to be generating two values. You've got your input here, and you're going to be generating some value. We haven't talked about how we're going to get to that value yet, but we're going to call the value that comes out of this mu. And we're going to call the other one sigma. The idea between the two is that mu is going to be the mean of our distribution. So if we jump back to here, again, this is some distribution which we haven't defined yet. We're calling it Z of I given X and phi, which is the output of this encoder. But what's sitting really in the middle here is some distribution. Just try and keep that in your head. So the parameters for this distribution are going to be mu and are going to be sigma. The mu is going to be the center of this distribution, at least for the case of the Gaussian distribution, and sigma is going to be the standard deviation, right? If you've got more parameters to your distribution, something other than mu and sigma, so like let's say that you've got a distribution which takes in 3 values, you can generate those values as well. Now, yeah, so here's that idea. So Q Z of I given X and phi is going to be is defined as some normal distribution. We're going to be passing in the mu, which we're generating from above, and we're going to be passing in the sigma, which is going to be generated from above as well. Yeah.
We also for unit share the parameters in the
So
No, no. This, that the right part.
yeah,
The 4 and the right 4 and the left 4.
yes. Are those shared?
Share the parameter.
No, they're different variables. So there could be a situation where, you're just trying to estimate, parameters into a distribution, right?
Yeah.
So you've got your mu, which could be, you've got your mu, which is trying to generate some center, and you're trying to generate then some standard deviation, which is relative to that center. So this mu could be all over your vector space. You have no idea where it's going to be, but your standard deviation is going to be within some range, right?
So parameter layers, mu and the standard deviation to the middle layer will not be fully connected.
This layer, so you can think about it as this kind of a bisection between the two. So you've got these four, at least in this case, these four nodes, which are going to be drawing from all the inputs and then predicting your mu. And then you've got these four, which are going to be drawing from the other ones and predicting your sigma. So they're independent. I suppose you could fix them.
Yeah.
I don't know whether or not that would give you better results, but in practice, every example I've seen, they've been. You could probably also do a fully connected one as well, but you'd need to make a distinction between the two. Every example I've seen, they've not been fully connected, or like this sigma is not drawing from these guys over here. But you can define your architecture however you want. The only thing is that you actually separate these two values out. So when you've got when you're actually going to generate values from your distribution, you're selecting these mu values only from the topmost values. So whatever's going on underneath, you could be, it could be fully connected or it could not be. Sometimes you can, so this is kind of just a generalization, but you can estimate the entire matrix if you want as well. But yeah, for the purposes of the slides, we're going to call it the diagonal. Any other questions? All right. So again, just to recap, your latent space is going to be drawn from a distribution, the parameters of which are estimated by the neural network. So you've got the parameters for the Gaussian, which is going to be the standard deviation, and our central and our mu, our center for that distribution. Yeah, so predicting these values, the outputs for our network are going to be mu and sigma. Again, if you've got a different type of distribution sitting in the center there, you can also use, you can use different parameters if you want. So we're going to refer to these parameters from now on as W1 and W2. So W1 is going to be the values for the mu, and then W2 is going to be the values for the sigma. Collectively, they're going to be called phi, and that's why we condition it on phi. Yeah. So they're technically, the slides define these two as two distributions, or excuse me, as two different networks. One is going to be U and one is going to be S. In practice, it's typically one big encoder and then U and S sitting on top of that encoder somewhere. Yeah. So that's kind of motivated by the feature extraction stuff that we talked about earlier. So yeah, so this latent variable, which we're going to be generating from our distribution, here, is going to depend in a nonlinear way on x, and then that's kind of how we get our representation. So this is kind of how we can think about it. We talked about at the beginning of the lecture that VAEs are kind of performing a nonlinear factor analysis. So in factor analysis, you're estimating two Gaussians or n Gaussians, and you're trying to draw a linear separator between the two based on the relationship between those two Gaussians. Here, those Gaussians are going to be operating in a projected space, and so, or here rather, the Gaussian that we're estimating is going to be operating in a nonlinear space because of the projections that have been working on top of it. So that's kind of how VAEs are doing nonlinear factor analysis. All right, so we've got that. Now we're going to talk about the decoder. In the decoder, we're going to do two different things. We're going to take in z of I, which has been now drawn from this distribution. So the slides kind of jump a point. So we've got the parameters here, mu and sigma, and that then generates a value z of I, some hidden distribution, or some hidden value drawn from that distribution. And then based on that hidden value, which we've talked about here, this z of I given x and phi, based on this hidden representation, we're then going to try and estimate the parameters to that distribution. This is kind of the classical VAE. What typically happens in practice as opposed to estimating the parameters to that distribution, you're just going to estimate the output. So as opposed to trying to figure out what your mu is or what your sigma is, you're going to try and estimate x of I, the input. Yeah, so we've got another two, W3 and W4. Those are collectively going to be called theta. Again, it's technically two separate networks, but typically in practice, you've got these two separate networks sitting below some fully connected decoder, which is actually going to be doing your decoding. Again, there's two different networks. U and S. We had U and S before, but this is U sub D for the decoder. And again, we've got that value that's been drawn from this distribution, and it depends in a nonlinear way because of the neural network. It depends on the latent variable. They don't have to use the same distribution necessarily, so you could have a totally different type of network sitting on top or sitting below. The idea is that you just want to relate the two. Basically looks like an autoencoder, but the outputs of the decoder are the parameters of the distribution. Typically in practice, you're going to be estimating the actual output as opposed to the parameters, but the idea is that from the parameters of the output, you can then generate the input to that distribution fairly consistently. And we've also got this sampling step in the middle, which is a little bit weird. So you're going to want to sample from that distribution. So we can combine these two, and we can use expectation maximization for training. So we've got, remember, we've got two things going on. We've got our Q distribution here, and we've got Z of I, and we've got two parameters. We've got phi, and we've got theta. So the idea being that in the E step, we're going to hold the parameters for the, which one is it? The decoder fixed, and then find the Q of T, and Q of T is the encoder, which maximizes we're going to be doing that maximization step. And then the M step, we're just going to flip the two, and as opposed to holding theta, we're going to hold that Q distribution, which is going to be this guy, and then find the theta that maximizes that value. So you can kind of play with it a little bit. You can use EM. This is, you can do this. This is kind of the relationship back to variational inference and factor analysis, but we can still do this with backprop, and we'll talk about that in a little bit. So in order to do backprop, we're just going to change notation a little bit. So as opposed to maximizing on Q, we're going to then maximize on the parameters of the other distribution. So if we jump back here, we've got phi and we've got theta, and we're going to be doing phi and theta. So fixing, holding, fixing, holding. So what it really comes down to in the end is that find the gradient that is then going to increase the relationship between the estimated lower bound as close as possible. And then this is kind of what we talked about. This is off of KL divergence from before. So now that we've got the gradients, we can then compute the loss. So loss, this is the derivation. There are two ways of doing it actually. The first is that I want to make sure I don't confuse these two. Okay. So the first is you can use Monte Carlo sampling to estimate the parameters drawn from or to approximate the expectation using the samples drawn from that distribution. So the idea is that this is going to be our encoder. We've got Z of I, X of I. So we're trying to, this is the encoder. So we're trying to generate some latent value. So we're going to draw samples from it using Monte Carlo, and then average them using, average them. And then that's the expectation. And then for actually computing the loss, we're going to be, there's two kinds of losses that we can use for this. This is the first one using Monte Carlo to estimate the values drawn from that distribution. I'm going to call that loss A. It's going to be highlighted in purple. I think this symbol might have gotten messed up in a couple of the slides, but if you see purple, this is what we're talking about. and it's just going to be defined as the differences between the two values. So estimating the probability of x of I, z of I, given some parameter theta, and then the log of the distribution q. So just average these two together, and then we've got our Monte Carlo loss. That's the first way of doing it. Yeah. The other way we can do it is we can compute these values analytically. So as opposed to drawing values directly from the distribution using the parameters, what we can do is we can actually use the parameters or generate values analytically, just generate some value that's associated with that distribution. And then we can use the parameters just mathematically to generate the values. So if you think about what's actually going on inside of a Gaussian or whatever distribution, if you're passing parameters to it, then you're sort of influencing the values directly. And so we're going to talk about that in a little bit, but this is kind of just to motivate that. So the other thing to think about, the other way to rewrite this is, as opposed to doing sampling and Monte Carlo things, we can just take this separate loss function, which, again, I think some of these might have gotten messed up, but as long as you see green, this is what we're talking about, as just the KL divergence and then the log probability of the data. The average log probability of the data. Yeah. Exactly. So yeah, if you have nicely defined data, or if you know your distribution fairly well, yeah, then you can compute these values analytically. But if you don't know your distribution necessarily, or maybe your distribution is defined in some weird way where you can't get these values analytically, then you can use Monte Carlo sampling to generate that, and then compute the loss from there. Okay, so with all of that defined, we can use EM to train the whole thing. Typically, this isn't done. Typically, we're able to use backprop, and we're going to talk about that in a little bit. But we can use expectation maximization to then train this model. So we're going to do two things. There's two steps going on: the expectation and the maximization. So we're going to try and estimate the gradient based on the loss and phi. So here we're fixing theta, and we're estimating phi. We're going to update phi, and then we're going to do the same thing, but for theta. And so, yeah, this is kind of hand wavy. We're going to talk about it in a little bit. But this is just kind of pseudocode. And the idea is that you're just going to sample from that distribution, and then you're going to run forward backward on the, you're going to run a forward, not the forward backward algorithm, excuse me, but you're going to run a forward pass and then a backward pass to calculate the gradients using one of these two loss functions that we've talked about before. And then you're going to update the parameters based on the gradient update step that we've talked about before. Yeah, and update them. And we're going to do this for all of our data. This is basically just saying, do some hand wavy thing, which we're going to talk about in a sec, and then do gradient descent. Yeah, I think this is where it got messed up. So this green value, loss tilde b, is this one, and then so. If you know your distribution, this green value right here is going to be the gradient computed analytically, whereas this one is going to be, or excuse me, the loss computed analytically, whereas this one's going to be the loss computed via Monte Carlo sampling. And yeah, for simplification, we're just going to, as opposed to drawing multiple different samples, we're just going to draw one sample and call it good. Supposedly you can get. Because you're doing this for all your data, this is going to average out, but you can, maybe get a slightly better estimation for it if you decide to, actually just take one sample for it, or take multiple samples for it. Excuse me. Yeah. Okay, so I've kind of been glazing over this point, but when we're doing a sampling operation, that's kind of inherently. You can't backprop through it very well. So if we're using standard backprop to estimate those values, to estimate the values in theta, we're not going to have a problem, right? Because we can just backprop straight into that. But the second we get to phi, we kind of hit a brick wall, which is that we can't get the derivative out of a sampling distribution. So we're kind of at a brick wall. And the way that we can get around this is that as opposed to using the parameters directly to generate the distribution, using the parameters that we're generating, that mu and that sigma, to generate values from that distribution, we're going to kind of use a trick. So as opposed to, I don't have the additional, the original mathematics, but if from what we were doing before, we have, let's say, a normal distribution, and we're passing parameters mu and sigma to it, and then we're sampling from it, right? The thing that we can do is we can just pre-compute a bunch of different samples from this distribution, and then as opposed to passing the parameters to it, we can generate some just some set constant value parameters going into a normal distribution, and then we can calculate analytically the sample that we want based on those values drawn. So because we've got this is the value that we're trying to generate. We've got mu and we've got our sigma. So mu and standard deviation. And if we do this, it's not backpropable, obviously. But if we generate a bunch of samples prior to doing backprop, use those samples, and then compute these values based on the parameters that we're using, then it just becomes multiplication and so on and so forth. Multiplication and addition, we can completely backprop through those. So it's kind of just a rewrite kind of trick on top of your data, or on top of that distribution to make this work via backprop. So we're gonna call this distribution eta, and it's gonna have parameters. It's gonna have a center at 1, and it's gonna have a center at 0, and it's gonna have a standard deviation of 1. If you want to, you can use different values, but this is kind of just what's used traditionally. So then, with that, we apply our values to it, and then we get the value that we were looking at before. So it's really just a rewrite trick, but yeah. Okay, so with that being said, we've kind of passed this brick wall, and now we can do backprop from start to finish. But instead of using z of I as the initial the thing that we're trying to predict, we're going to be using this eta, which we just talked about right here. So as opposed to sampling, we're just going to be computing the samples either at runtime or at just ahead of time, and then using those samples as sort of a seed for the variables that we've been generating, or excuse me, for the parameters that we've been generating. So we can backprop through this now. And so now we've got our E step and our M step. So in the E step, we're going to be we're going to be estimating the gradient of the loss with respect to phi, and we're going to be fixing the parameters for theta. Fix, estimate, and then we do the reverse. So estimate now for the parameter, the gradients for the theta, and then use standard backprop with the parameters for phi fixed. And we're going to use whatever loss function we've got. So if it's a crazy distribution that we don't necessarily know, we can use a Monte Carlo sampling, or if it's a distribution that we know pretty well, we can use the analytical solution. Full training procedure. So the EM procedure isn't traditionally used. Typically, we just backprop this whole thing. So we estimate the loss for all the things based on whatever loss function we've got, and we update the parameters for each one at the same time. This is just standard backprop. Because these loss values are defined a little bit weird, we can just use the -1 and call it good. Run whatever gradient descent variant you want. At this point, it's just a neural network with some math in between. Running the model on new data. So you can use the mean output of the encoder so if you're doing multiple samples, then you can use the mean output. at test time, this is just, you don't do that. You just pass the values directly as opposed to generating means. Yeah, and you can generate multiple samples if it's if you're about introducing some element of randomness into your model. You can take n samples from that distribution and run the decoder multiple times and then average those or something like that. There's a bunch of different ways you can go about it. Yeah, and you can use that to estimate uncertainty as well. So if you draw a bunch of different values from this distribution and you find that the values that your network is generating are wildly out of whack, then you can know that, hey, this is either I'm not doing a good job of estimating these values, or there's a great deal of uncertainty in this data, at least with the training state being where it is. So VAEs perform probabilistic because it's conditioned on a distribution. Nonlinear dimensionality reduction. So we're going to be doing some nonlinear operation and condensing that data down into some hidden latent representation to actually get the data. Yeah. So the observed variable is this conditional probability. We're going to be regenerating it from that. Training is approximately running expectation maximization. So we kind of talked about how you could fix the two, or fix the encoder and then train the decoder, and then fix the decoder and train the encoder. Kind of doing that expectation maximization. But for all intents and purposes, you can train both and update both at the same time. So with all that being said, this is basically just nonlinear factor analysis for an encoder-decoder model. Yeah. You can regularize using some prior. So if you've got your KL divergence right here, you can use this log prior here, x conditioned on z and the parameters. Yeah, and so you can use that as kind of a divergence, or excuse me, as a bias or a regularization term to try and account for some of the variability that's in your data, or excuse me, variability that's coming out of your sampling distribution. Yeah, this is basically just doing maximum likelihood maximum likelihood estimation regularized by a prior on the latent space. So yeah, this is the okay. Practical advantages between a traditional autoencoder versus a VAE. The latent space, because you're choosing a distribution that's going into the latent space, you have the chance to give some domain knowledge to your model. So if you know that some of these values are based off, some of your data is based off of a Gaussian or based off of some other distribution that's going on inside, you can kind of inject that to your model. You can also use it to make the latent space a little bit more interpretable. So we're conditioning these values on a Gaussian or on something else. So that means that we're going to be trying to, form these together. Yeah.
I think those distribution is very limited and very simple compared with the data's domain knowledge, the domain knowledge from the transfer learning community. So is there any methods to transform those domain knowledge, those non-parameterized distribution into this way?
So like you've learned some distribution already, and you're trying to generate samples from that, but you don't necessarily know the parameters to that distribution. Yeah. The best way that I could think about it is that you could take whatever distribution that you've learned empirically and fit it using some curve or something like that, and then estimate the parameters to that curve using this method. Does that make sense? There's not really a way to do it if it's purely empirical. Yeah.
I guess if you have a distribution, you're talking not one value but multiple.
Mm-hmm.
Suppose you have something like a count variable and things like that, and you may not necessarily have a good joint distribution for them to
Yeah.
look at P. I would think that the copula theory might come in here somehow.
I'm not familiar with the copula theory.
It's basically a way of splicing together together variables that come from different, you think they come from different statistical distributions, and created samples from joint distribution.
Gotcha.
So
That actually makes some sense. Yeah, I'd have to check the math, but it seems like that would be something that would work reasonably.
populism can afford on its own, but that's why Gaussians are kind of nice here. But if you're stuck with the variables that you have one count thing and they have one continuous thing, you need to actually calculate joint. Then the copular theory on the kind of when you feed it into encoder like look up.
Gotcha. Sounds like a research paper. All right, so then with that, you can also use this to estimate the variance and the uncertainty in your predictions. So if you have, like I said, so if you sample a bunch of times from your distribution in the middle and your latent or your decoder is just behaving completely erratically, then you can kind of make some estimations about how uncertain your model is for this parameter, for this data. But if you sample a bunch and the data is all pretty similar, then you can tell that your model's doing fairly well. So what does this look like in code? I know that we've kind of just stepped through all of this crazy stuff, and it may not make any sense on how to actually do this in code, but it's really straightforward. So this is this is PyTorch. And so this is basically an implementation of what we talked about earlier, with the exception of that, as opposed to trying to regenerate the parameters to the distribution in the decoder, we're just trying to estimate the input directly. So we've got one fully connected input unit. We've got another fully connected input unit for estimating the mean, and then another for estimating the standard deviation. Then we've just got two additional fully connected units sitting on top of that. And then we've got two activation functions. Fairly straightforward. So we've got our so we've got our encoder pass, which is going to generate some hidden value based off of the ReLU activation of the first fully connected layer, right? So we've got one fully connected layer up, and it's using ReLU. So straightforward so far. And then we're going to return two values. One is going to be based off of that hidden value generated from our fully connected layer. We're going to return two values. One is the activation returned from the first fully connected layer, and the second fully connected layer is the second one. So fully connected input, fully connected layer, and then two fully connected layers sitting on top of that. We're going to do this reparameterization step, which is then going to take in some mu and the variance. Some people call it the standard deviation, some people call it the variance, but you're estimating the parameters, so however you want to do it. If you wanted to actually you pass the standard deviation or pass the variance to your Gaussian or whatever distribution you can. So reparameterize is going to take the mu and the variance. So here we've got our encoder. Based off of the input data, we're going to generate some center and some variance or some standard deviation. And then we're going to pass that to the reparameterize step, which is going to generate some hidden distribution z based off of some distribution Gaussian here. So we're going to be taking we're going to generate the standard deviation from our log bar here, and then we're going to generate this thing called they call it EPS. But you just generate a normal distribution across your data. And then you just do the math to draw a sample from that distribution, right? So we've got the encoder generating a center for your distribution and in this case, a variance for your distribution. You then use those two values as parameters to draw a sample from that distribution. And then now you've got your hidden representation z, and then you're just going to run your decoder, and the decoder just takes in z, does a ReLU of a fully connected layer, and then spits out the signal to the next layer, right? And then at the end of your forward, you return, in this case, you return your decoder, and then the parameters to your distribution, so you can recompute it if you want to. I know we went through a lot of math to get to this point, but this is the main idea. When I first learned about this, it seemed kind of crazy to me that you were using. It didn't make sense to me personally how you were able to get to the parameters of your distribution from your network. But there's no crazy magic going on. You're literally just estimating parameters to a distribution directly from your network. And then you're using a bit of math to get around the differentiability of different sections. Yeah.
Why did you use the sigmoid activation function?
I believe this example was for MNIST, and so all of the this was just the pixel values. You know, if you're trying to generate a real value or something else, you can use a different activation function. But yeah, I don't think there was anything special going on. Okay. All right, so then this is an example of what these distributions actually look like. So here we've got MNIST values. So the labels for each image are here, and the colors are representative. And so, you know, the VAE will kind of sort these into clusters a little bit. And you can kind of see the projection of this data. So this is a 2D latent space based off of that Gaussian distribution. So yeah, based off of this parameter here. And then, you know, you can actually see that they're kind of clustering around each other. In a traditional autoencoder, this behavior wouldn't really be seen. You might see some clustering, maybe a little bit, but your data would be fairly interspersed or interleaved, kind of like what's going on here. So in the case of, it looks like red and green, it looks like it's 5s and 4s, and so you can kind of see why those would be confused a little bit. Oh, 9 and 4s. Oh, yeah, that makes even more sense. Yeah. So yeah, the other cool thing about this is that because it's a generative model, we now, you know, even though we don't have data in this bottom left corner, we can kind of, oh, that's actually a terrible example. Because we don't have data sort of in this area, we can kind of see a blending between 1s and 7s. And so it's, even if you're putting, you know, random values into this latent variable, into this generator, you're still going to get values that sort of appear to have been drawn from your original distribution. We're going to talk about utilities, you know, ways you can use this later on with GANs, but that's kind of just the idea. So now, how can we look at this latent space and interpret it a bit? One of the cool things about VAEs is that it lets us kind of estimate what's going on in the latent space, and we can sort of based on the behaviors of each Gaussian, we can use from each space and parameters generated for the distributions to calculate vectors for, you know, different components. So here, this is the celebrities data set, but we can, you know, take a vector that we've estimated from all of the you know, the average of all of the samples that have, you know, people smiling, and then add that vector onto some input. And, you know, because we're using Gaussian data, which is somewhat, you know, we know what's going on and we can interpolate a little bit between the distributions. We can do things like, you know, introducing smiles or introducing sunglasses or something like that into these autoencoder examples. So, you know, in this case, as opposed to you generate some representation using your encoder, and then you already have some learned representation for what sunglasses or what smiling means. You can then add those two hidden representations together, and then pump it, normalize, and then pump it through your decoder, and you get stuff like this, which I think is kind of cool. Yeah, so there are two things that you need to know. The distribution must be easy to sample from if you're doing this. So we kind of talked about that a little bit. And the conditional likelihood must be computable based on the, you know, based on your parameters to your decoder and the hidden space. Basically, that's just saying if your distribution that you're using is completely disjoint from the distribution that that this data was drawn from, then you can't really use this approach. But for the vast majority of cases, especially with autoencoders, if you're just using a Gaussian, your data is going to look somewhat good. Yeah. So you can use a bunch of different distributions: uniform random, Gaussian, isotropic Gaussian. As long as it's centered around some point, you're going to be doing just fine. So one of the problems that's introduced by VAEs is the fact that images that come out of it are often blurry or fuzzy or something like that. At least in images are a great way to look at, visualize your your data. But there are a couple of reasons that could be causing this, and the obvious one that's different is the fact that you're doing a sampling operation in here. So if you tend to see blurry images in your output data, one of the things you can ask as, or think about as a cause for it is the fact that you're just, your model's very uncertain about the distribution that's going on. So if you're sampling from it and you're getting a bunch of blurry values out, then you can kind of think about that being a cause for this. Yeah. There's a whole blog post and paper on this problem, but it's something that comes into play, but don't be surprised if you see it. This is just a bit of appendix stuff. Investigations of blurriness, and I believe that's the end of the lecture. Right. Really? I'll say that I planned that. Alrighty. Any final questions? Alrighty.